going to study about LC oscillations. It consists of an inductor and a charged capacitor which are connected so that this circuit exhibits electrical oscillations of constant amplitude and frequency, and such oscillations are called LC oscillations. So LC oscillation means it consists of, the circuit consists of an inductor and a fully charged capacitor which are connected so that this circuit exhibits electrical oscillations of constant amplitude and frequency. So when a charged capacitor is connected to an inductor, the electrical oscillations of constant amplitude and frequency are produced, and these oscillations are called LC oscillations. Now we can explain the qualitative explanation for the production of LC oscillations. So consider a fully charged capacitor is connected to an inductor through a key. Let the key is open. Okay, let this key is open. Now here this is a fully charged capacitor. It stores the maximum charge. Let the maximum charge be Qm. Okay, charge is maximum Qm. Here the capacitance is C. Here the inductance is L. So here no current flows through the circuit because the key is open. This is an open circuit. And what is the use of the capacitor? We know capacitor is used to store electric charge. Okay, and the energy stored in a capacitor is given by half Q square divided by C. Q square divided by 2C, that is the formula. So energy stored in the capacitor, that is in the form of electrical energy, is Qm square divided by 2C. Here inductor, no current flows through the inductor. So what is the energy stored in the inductor? Energy is equal to 0. So first figure is fully charged capacitor is connected to the inductor L. Electric energy stored in the capacitor is Qm square divided by 2C, and since there is no current flowing through the circuit, magnetic energy stored in the inductor is 0. Second case, if circuit is closed, capacitor begins to discharge. That current passes through the inductor. Okay, capacitor begins to discharge and that current passes through the inductor, and around the inductor produces magnetic field. Okay, so here the energy stored in the capacitor decreases and energy stored in the inductor, initially it was 0. Now inductor energy stored in the inductor slightly increases. Okay. Now the capacitor begins to discharge. Okay, key is closed, circuit is closed, capacitor begins to discharge producing a current I. This current increases, or this current passes through the inductor L. So what happens to magnetic field? Magnetic field increases, and hence energy is stored in the inductor now. So energy stored initially, energy stored in the capacitor was maximum. When it discharges, energy stored in the inductor decreases and energy stored in the inductor increases. So now the energy stored in the capacitor is Q square by 2C, and the energy stored in the inductor is half Li square, and this represents the magnetic field around the inductor. Now after some time, at a later stage, capacitor gets fully discharged and the current becomes a maximum value, that is Im. Capacitor is fully discharged and hence the potential difference across the capacitor becomes 0, producing a maximum current Im. Now the magnetic field around the inductor becomes maximum, so energy stored in the inductor is half Lim square, and the energy stored in the capacitor is equal to 0. That means the total electrical energy get converted to magnetic energy across the inductor. Then after the discharge of capacitor is complete, what happens? The magnetic field linked with the inductor decreases. Initially it was maximum, now no current is coming, capacitor is fully discharged. So what happens to magnetic flux linked with the inductor? It decreases and it produces an induced current which charges the capacitor in opposite direction, opposite polarity. So bottom plate becomes positive and the top plate becomes negative. Okay, so now the energy stored in the inductor is UB equal to half Li square, and energy stored in the capacitor is UE equal to Q square divided by 2C, and electrical energy stored in the capacitor is Q square by 2C. Again this process continues till the capacitor is fully charged with opposite polarity. So after some time capacitor gets fully charged but in opposite direction. So bottom plate becomes fully positive charge and upper plate becomes fully negative charge, and the energy stored in the inductor is 0 and energy stored in the capacitor is Qm square divided by 2C. Okay, again the process continues. Again the capacitor begins to discharge, again the inductor the magnetic energy stored in the inductor increases and the process continues. So, electrical energy can be converted to magnetic energy and magnetic energy becomes electrical energy and the process continues. So, it is similar to a simple pendulum oscillation. You know simple pendulum oscillation, if a pendulum is oscillating between the two extreme positions, at the two extreme position it has which type of energy? Potential energy. At the mean position it has which energy? Kinetic energy. So, when it oscillates from mean position to extreme position, kinetic energy converts to potential, and when it moves from extreme to mean position, potential energy becomes electrical. So, one form of energy is converted to another. So, that is the mechanical oscillation. But here in an LC, inductor and capacitor, in LC oscillation, electrical oscillations are there. Electrical energy stored in the capacitor is converted to magnetic energy stored in the inductor and the process goes on. So, it is similar to the mechanical oscillation of a simple pendulum, or it is similar to the mechanical oscillation of a suspended spring. Okay, but here the change is LC oscillator exhibits what type of oscillation? Electrical oscillations. Thus, energy of the LC oscillator continuously oscillates between the electric field of the capacitor and magnetic field of the inductor. So, as discussed, electrical energy of the capacitor be converted to magnetic energy of the inductor, and again magnetic energy becomes electrical energy. Okay, this process produces electrical oscillation of definite frequency, which is given by omega equal to 1 by root LC. This is similar to the resonant frequency in a series LCR circuit. But here the amplitude of oscillation, normally if you consider the amplitude of LC oscillation become damped. Damped means amplitude goes on decreasing due to some reasons. First reason is the inductor has some resistance. Okay, so when electric energy becomes magnetic and magnetic amount energy becomes electrical, some amount of energy get converted to heat because of the resistance of the inductor. And again some energy radiated away in the form of electromagnetic radiation. During transfer of electric energy to magnetic energy and magnetic energy to electrical energy, some amount of energy gets converted to some electromagnetic radiations. So, that is the reason why in an LC oscillator amplitude will not be a perfect constant, amplitude goes on decreasing. Okay. A numerical, a charged 30 microfarad capacitor is connected to 27 millihenry inductor. What is the angular frequency of free oscillations of the circuit? Okay, so capacitance is given as, what is the value of capacitance? 30 microfarad, that is 30 into 10 raised to minus 6 farad. Inductance is 27 millihenry, that is 27 into 10 raised to minus 3 Henry. We have to find out the angular frequency. We have angular frequency omega equals 1 by root LC, because this is an LC circuit. Angular frequency is given by omega equal to 1 by root LC. We can substitute root of L, 27 into 10 raised to minus 3 into capacitance is 30 into 10 raised to minus 6. And after simplification, you will get the answer as 1.1 into 10 raised to 3. Angular frequency, no? So, what is its unit? Radian per second. Clear? Next question. An electric lamp connected in series with a capacitor and an AC source is glowing with certain brightness. How does the brightness of the lamp change on increasing the capacitance? So, how does the brightness of the lamp change? Brightness depends on current. Okay, and current depends on resistance. So, now what is here? A lamp is connected to a capacitor. So, what is the resistance offered by the capacitor? We have resistance offered by the capacitor is capacity reactance Xc equal 1 by Z omega. Clear? And here what happens? The question is, how does the brightness of the lamp change on increase in the capacitance? So, if capacitance increases, what happens to capacity reactance Xc decreases. Okay, capacitance increases means Xc decreases. Xc means the resistance, the total resistance offered by capacitor to AC current. So, capacity reactance decreases means what happens to current? Current increases. Current increases. Current increases means what happens to the brightness of the bulb? brightness of the bulb increases. Clear? Clear, children? So, capacitive reactance is 1 by C omega. As capacitance increases, capacitive reactance decreases, and capacitive reactance decreases means what happens to current? Current increases, and hence brightness of the bulb increases. A chalk coil and a bulb are connected in series to an AC source. The bulb glows with certain brightness. How does the brightness of the bulb change on inserting an iron core in the chalk coil? So, a chalk coil means an inductor, a solenoid. An inductor and a bulb are connected in series. So, this is an inductor and a bulb are connected in series to an AC source. This is the question. Now, in the question itself it is given the bulb glows with some brightness. How does the brightness of the bulb change on inserting an iron core? We have the resistance offered by the inductor. Resistance offered by the inductor is called inductive reactance equal to L omega. We have XL equal to L omega. On inserting the iron core, we know that self-inductance L is given by mu 0 N square AL. This is the formula for self-inductance. Clear? Now, on inserting iron core, what happens to self-inductance? On inserting iron core, self-inductance L equal to mu 0 mu r N square AL. That means self-inductance increases. L increases. L increases, what happens to XL? XL, according to the formula, XL increases. XL means the resistance. XL increases means what happens to current? Current decreases, and hence brightness of the bulb decreases. Okay, so self-inductance is L equal to mu 0 N square AL, and we have inductive reactance XL equal to L omega. On inserting the iron core, self-inductance increases, XL increases, current decreases, and hence brightness of the bulb decreases. An inductor L is connected in series with bulb to an AC source. How does the brightness of the bulb change when number of turns in the inductor is reduced? A capacitor of Xc equal to XL is included in series in the same circuit. So, here an inductor is connected in series to a bulb and it is connected to an AC source. How does the brightness of the bulb change when number of turns is increased? Number of turns is reduced. We have XL equal to resistance offered by the inductor is given by XL equal to L omega. And what is the value of L? L equal to mu 0 N square AL. So, what happens if number of turns is reduced? Number of turns is reduced means small n represents number of turns per unit length. So, number of turns reduces means number of turns per unit length also decreases. So, if number of turns reduces, if number of turns is reduced, number of turns per unit length also decreases. N reduces, and what happens to self-inductance? And hence self-inductance, what happens to self-inductance? N reduces means self-inductance also decreases. Self-inductance decreases means what happens to XL? XL also reduces. XL means the resistance offered by the inductor, and hence XL reduces means what happens to current? Current increases, and hence brightness of the bulb increases. That is the answer. Brightness of the bulb increases. Okay, so that is the first part. Second one, a capacitor of Xc equal to XL is included in series in the same circuit. So, here if a capacitor is connected and the capacitor having capacity reacted equal to XL. So, second case is if Xc equal to XL is included in the circuit, we have the total impedance Z equal to root of R square plus Xc minus XL the whole square, isn't it? But here Xc and XL are equal. When Xc and XL are equal, here Z is equal to R. That means the total resistance decreases, and hence what happens to current? Current increases. This is the condition for resonance, no? So, current increases, and hence brightness of the bulb increases. increases and the bulb brights with maximum brightness. Clear?